Hello and welcome back to Gaming Like It's 1979. Today we are returning to the retro world of Last Call BBS and its minigame Chipwizard Professional. Let's take a look. So we go on to Drive 0, and as you may remember, Chipwizard Professional is an updated version of the very old, I'm sure the Zacks are depressed to hear that, the very old circuit drawing game, Constructor Engineer of the People. Now that Flash is basically unusable for most of us in the modern world, we needed another way to get our fix, and that leads us to Chipwizard Professional. So we will be starting on this second column of puzzles today. We're going to be going through the entire second column in this video, and we're going to start with Ignition Sequencer. Alright, so let's look at the problem here. When run is activated, each output should activate with the indicated timing, delays of 2, 4, and 8 cycles. So this is one where you really want to look at the simulator to understand what is being asked of us. And what we see is that the run input goes high and stays high for some period of time. And then we have these three outputs, which all are high for the entire time that run is high, but they start at a delay. And the key thing here is that they go low the instant run goes low. I think that's true in every case, which makes me wonder, could we do this without any sort of transistor? Could we just use run to make this happen? I don't know. I've never tried this before, so let's give it a go. I've never tried this solution before, but now I'm curious to see what's going to happen. So can we do this with just bare metal is basically the question. So we know that we're going to need delays, right? So this one wants a delay of 2, 1, 2. This one wants a delay of 4, 3, 4, and this one wants a delay of 8, 5, 6, 7, 8. And in fact, let's do that. Can we just do this? This can't work. There's got to be some reason why a transistor is actually necessary here, but let's try it out. Let's step through. Okay, run is not high. Now run is high. 1, 2, and out is high. 3, 4. 5, 6, 7, 8. That looks good. Will it work on the downside? It seems to. Great, we've made a circuit with no transistors. And somehow I still don't have, with literally almost no silicon, I still don't have the best score. Do I want to try and make this even more efficient? No, I don't. I'm not going to waste your time with it. That is left as an exercise to you. Well, I didn't think that a transistorless circuit was possible for this. It's nice to know that it was. Now we're working on the equality tester. Out X, which is over here, should be high when in A and in B are equal, either both high or both low. So in circuitry terms, we're being asked to make an XOR circuit. Now, here's where I think Chipwizard Professional gets a little... it feeds into my main complaint about many of the Zack games, is they get their difficulty or their challenge from the fact that you have very constrained space to work with. If we were doing this, as a normal circuit, we would have essentially an infinite, or so big we could treat it as infinite, breadboard, and we would put down an AND and a NOT gate. And we'd wire everything up and we'll be done. But what we're going to see here is that with only, let's do 5 times 6, with only 30 spaces to work from, and many of those effectively being dead spaces, getting an AND and a NOT gate into this space is actually going to be where all the challenge is. So let's proceed carefully. So first of all, we know that the output has to be high when both of our inputs are low. So that tells us that we're going to need some voltage. So I'm just going to pull that out there. I don't know if that's the right place for it, and we might have to pull it from one of the other places first. And we know we're going to need an AND gate and a NOT gate. So, and we know that those AND gates and NOT gates, assuming we don't have to be too clever, which we don't know yet, they're each going to have 2 inputs. So that means they have to be this big. And again, I'm just going to put I'm going to try and pick the right silicon there. I'm just going to put them in the middle. And, you know, we might have to revisit this as we do our design. And then this is going to be our NOT gate. And we're just going to go ahead and, so we don't forget, put vias everywhere. All right. So right off the bat, we know, again, because there has to be power when they're low, when they're both low, then we know that they're going to both need this on one end of these transistors. They're going to need power. So that feels like a gimme. And we know there needs to be a wire going to output here, right? And that wire needs to be high when either of these outputs is high. And there's a transistor on the left side of them, so we don't have to worry about those interfering. So we can just do that. So far, this is looking pretty neat. Where's the catch? There's got to be a catch, because this can't be as easy as all that. And the catch is going to be bringing the signals from in to these on silicon. So because this metal is here, we can't just bring that across because it would interfere. So it's got to be on silicon. Well, we know we want this one to come here, right? So instead of having a via here, let's pull this all the way there. Okay, so that one's done. Same thing here, I think, right? Yeah, let's pull that over here. Right, and this sort of nonsense, I mean, you wouldn't do this, right, on a real circuit board. You would pull that V around on the other side of it, and, you know, or in a third dimension, and it would be fine. Okay, so that's that. But now we have to bring, I'm going to actually start advancing there. So now we want to bring this signal here, this in A signal. Love the X Windows cursor when you're in the middle of a simulation. We want to bring this one to this input. And we want to bring this over here. I think we can do this. So the problem is this is a crisscross. And so we could easily bring one over there, but not necessarily the other. So again, right, okay, so I think what we have to do is one or the others of these has to move, similar to what we did with their partner. So let's move the second one, because I like blue more than red. Why not? Okay, and then a via there, and a via here. Okay, so the thing to remember is that this funny U-shaped bit of silicon for both cases is equivalent to in A and in B. In A and in B. So we can now just bridge those with wire and then bridge those with wire. And I think that will work. Maybe. Let's find out. Oh, good. I'm so happy that worked. Again, wow, not at all the most efficient solution. And one of the readers actually replied to the comments in the last video. Thank you very much. If you have comments about this video, leave them in the comments below on YouTube. And what they said is that the score is determined almost entirely by the square area of silicon. That doesn't quite track to me because we used capacitors. So maybe capacitors count as silicon in this case. So you could see we're using a lot of these, we're pulling out a lot of silicon here to accomplish this. So clearly there's a more efficient way to do it, and spoilers, I don't care. Dual oscillator. The fast and slow outputs should oscillate with the indicated timing, periods of 2 and 6 cycles. So looking here, we've got one off, one on, one off, one on, one off, one on. That's the 2 cycle. And 3 off, 3 on, 3 off, 3 on, 3 off, 3 on. The other thing that's worth noting here is that these cycles seem to be matched. So we might be able to do something clever with a single oscillator and simply multiply it. I don't know. Let's try just doing the fast oscillation first. Oscillation. So whenever you hear oscillation, it's oscillation, I know that. You definitely want to think of a NOT gate. So let's remind ourselves by viewing the manual of what our transistors are. P and P are the opposite. They only allow signals to flow when the two red terminals, between the two red terminals when the blue gate is not powered. Okay, so it's red, blue, red is what we want. I knew that, but I figured it's good to have a reminder. So let's go ahead. You know what? Since I'm just doing it for the fast one, let's just go ahead and use all the space right in the middle here. We're not going to worry about it. All right, so our power is going to come. We'll move it later, and that'll give us a chance actually to show how to move elements on these circuits, which is useful to know. So we're going to power it with our voltage. There is no input, there's just the voltage. So what do we want? Well, the interesting thing is we know that this thing wants to start in the off position. So if we connect it that way, and let's go, it will start in the on position. So we know right off the bat that this is wrong. So we could introduce a delay. Let's go ahead and introduce one capacitor and see what happens. Okay, now it's off. Now it's on. Great. And obviously, we can turn this off by bringing this circuit down here. So let's try that and see what happens. Spoiler alert, it doesn't work. Why doesn't it work? Well, let's watch what happens here. We're off. We've introduced a delay. And in the instant that we press, I'm not advancing twice there. The instant that we click play, it shuts off. Because we're doing it within that same kind of clock cycle. So logically, we need another delay right there. And if we do that, we get the oscillation we expect. So clearly, we have kind of 3 branches up here, right? We have a delay that applies on the on path, and on the on path before the power has gotten there, and then a delay that happens kind of after this branch here. So we could definitely add a second transistor with 3 in the pre-on path and 3 in the post-on path, 3 capacitors, and that would work. The interesting question to me is, could we do this and only use one capacitor? You know, I don't think we could, because as we've seen from this, the instant this input goes high, all the power kind of drains from this. So even if we pulled a new branch and fed it down here, I think at each of these off cycles, it would shut this off. So I do think we actually need a new capacitor. Oh, over here, right? That's 1. I'm going to pull this. You can pull it from over here. Why not? And then this is going to go here and there and there, right? Let's make sure that should be exactly the same as what we did before. It is great. Now we have to do the same thing down here, but we're going to need more space, I think. So let's draw it the same way, but over here. And we'll pull some wire there. And 1, 2, 3, 4, 5, 6. Right? I think that's right. And we can see 1, 2, 3 goes up, 4, 5, 6 goes down. That looks right. That's our dual oscillator. Safety interlock. Each output should be high. The outputs are here when its corresponding input is high and the other input is not. The alarm output should be raised when both inputs are high. So I always look for a few things when I'm reading these descriptions. And the first thing we note here is that for all of these cases, all of these out cases, at least one input is high. And the implication of that is that we may be able to solve this without using the voltage. Not something you would do in real circuit design, but I think we could do it here. So these are each clearly a NOT gate, and this is an AND gate. And again, this is an example where this would not be fun. I give Zachtronics grief because so much of this is jigsaw puzzling, but the reality is this would not be a fun problem if you had unconstrained space, right? If we had an infinite breadboard, you'd put down 2 NOT gates and an AND gate and you would be done. And instead, we're going to find there's going to be some challenge fitting these in, I suspect. So we know that this is going to be our AND gate. Let's go ahead and just put it there. I'm confident this won't work. This is going to be a NOT gate, right? And then this is going to be a NOT gate. We'll go ahead and put vias everywhere. All right, let's do out A first. I always like to do that, to just do the naive kind of, right? And let's make sure out A is this line here. Okay, and that's correct. Great. Well then, out B should be the same thing, right? And already we can see that the problem here is going to be pulling the wires across each other, right? Well, maybe not, right? So this one is easy. That's going to go there. And that's straight across. So the only problem we have left is getting this in A signal to here. So maybe we can just pull that silicon a little further and put another via and do that, right? Okay, great. Let's make sure out B is this signal here. That's correct too. So now our last challenge is going to be getting this over here. We can already see I've screwed this up horribly because there's actually no, well, no, I could do that. So that is not too terrible. So we want one of these poles to be in A, one of these poles to be in B, and one of them to be the out pole, right? Oh, actually, maybe this is easier than I thought. So we can pull our in A from right here using metal only, right? That is still in A. And we can pull our in B from here using metal only. And we can draw that straight to our alarm. That should be an AND gate. That's less messy than I thought it was. And in fact, we're going to get to play with the scoring here because I'm going to try and make this a little more compact for my own interest. But first, let's see if it works. It does work. That's great. And our design size is 25. That's better. So what I want to know is, let's get rid of this. Let's get rid of our metal here. Yep, not that much metal. Does the design guide, is it just the number of squares that this occupies? And someone already answered this, and I feel like I still don't understand it. But if I scooch this over, right? Is that as far as I can scooch? It won't let me scooch any further. I'm going to have to take this away and redraw it, looks like. Right, if I just make this compact, does that make a difference? I can't imagine it would. I would expect it to be exactly the same. Well, let's find out. It does make a difference. So it's not just the number of squares of silicon that are occupied. It's kind of the whole kit and caboodle. If you drew a square around every place there is silicon, you get, in this case, 15 squares, 3 times 5. So logically, maybe we could somehow make this even more efficient if we could get rid of, no, it would still be a square. It would be, I think 15's got to be the minimum here. I'd be very impressed if someone did better than that. So now we know how it works. So that is the safety interlock. PWM Solenoid Driver. I actually encourage you to Google some of these terms if you don't recognize them, and it will explain what they're intended to do. When hold is activated, the coil should be powered for 4 cycles and then begin oscillating until hold is deactivated. So looking at our test case here, the thing that jumps out at me is that whenever hold is not pressed, there's no power. So that suggests we may not need V. We may not need voltage to do this. So let's lay down powered oscillating. Whenever you see something's oscillating, it's a NOT gate, isn't it? Well, let's go ahead and lay down a NOT gate. And hold is what's powering it. So hold is going to be the input to that NOT gate. And if we run this now, what we see is we're always powered because I'm never actually turning it off because we're never not oscillating. Right? So hold could also be the input to our NOT gate. And what that should do is it'll be low all the time, right? Yeah. So we want to delay the shutoff, and we want to delay it by 4. Well, here's 4 squares. Is that right? Let's find out. Oh, this is also wrong because we're managing to have that up at all times. So that's wrong too. Well, let's still see what we get here. Did I make an AND gate? Did I manage to screw this up? No, that's a NOT gate. No, it's not. It's not any kind of gate. What hath I wrought? I've done something very wrong here. I need to reset my brain. Yeah, like a dope, I'm connecting this to plus V, which it turns out if you connect both sides of a transistor to voltage, it doesn't work so well. Okay, that's a little more sane. So what we're seeing here is that we are actually getting the wait 4 cycles before beginning your oscillation behavior. We're just not actually beginning the oscillation, right? 1, 2, 3, 4, and then it shuts down. And it shuts down on the 4th cycle. 1, 2, 3, 4. Right. Great. But we actually want to do an oscillation here, right? So this is clearly wrong. This part is wrong. We don't want that. We want an oscillator hooked up to that. Let's do this. We'll put these 1, 2, 3, 4. Okay, so over here we need to actually be oscillating. So logically, that's going to be a NOT gate. Let's make a little more room here. That's when the oscillation is going to begin. That's going to be our output, and that's going to be on initially. Something like this. I don't know if that's right. Let's take a look. 1, 2. Already very wrong. Why? Oh, because I have that in the wrong branch. Ugh. So let's rewire this. You know what? We don't have to rewire it. Let's pull this. Let's use our resizing powers. Repositioning powers. And reposition this. I guess I can't do it while I have all these wires connected. Right? Okay. That's totally not going to work. Well, is there any way I could fit it? Here. 1, 2, 3, 4. I think if I pull that, and then what I want is the output to come here, but then it also needs to come, I guess I have to go that way. So that's the on oscillation, that's the off. Let's try it. We're off by 1. We're very close. We are getting an oscillation here, but let's try it. Okay. So we want that first one to be off. I see. Actually, I think what we've done here is by putting this here, we've actually introduced a 5th cycle to that start session. So I think if I just remove one of these, and in fact, let's just put them over here so that we're minimizing our silicon. And then I could remove that one. I guess I do still need, I guess I'm overthinking this. I removed one in total. I confused myself by removing those guys. But by removing one in total, okay, great. Oh, that one was tough. Oscillations naturally don't fit into my brain. I think most people find them difficult. That's our PWM Solenoid Driver. Electronic lock. We have 5 inputs. 1, 2, 3, 4, 5. Open should be high when code 2, 3, and 5 are high, and code 1 and 4 are low. Low, high, high, low, high. Extremely unhelpful. Open is here. I'm going to go do that so I don't make the same mistake I made before and draw it from the wrong place. So 2, 3, and 5 are high, means there's an AND for all 3 of those. So the naive way to start would be to do something like this, right? 1, 2, 3. But there's no voltage here. And really any of these could serve as the input to this AND gate. So instead of doing a 3-input AND gate, I mean, logically it's still a 3-input AND gate, I guess, but instead of doing that, what we can do is do a 2-input gate and make one of these the power, essentially, to it, right? And codes 1 and 4 are low. So 1 and 4 going low, we would make one of these the power to a NOT gate, and the other the gate controlling the actual gate part of it. I think of that, that's how I think of these transistors. I think of one as being powering it and the other as being actuating it. Not at all accurate. It's just how it fits in my brain. So again, this is a space constraint one, right? And this is going to be our output. Well, we could just pop code 3 right here because it's here. And we can pop code 2 here because it's here, right? So that leaves us with how do we fit a NOT gate in here? And the thing that I'm noticing is that this could be the output of a NOT gate, right? And 1 and 4 are our inputs to that NOT gate. They're going to be low, so they can't power the NOT gate. And then 4 would go right here, I think. Right. And then, well, now that I know that, oh, I'm kind of doing this too much, aren't I? Right? Yeah, that can be over here. And then we're going to have a crossover here, I think, sadly. No, I'm doing it again. I'm just not seeing these. You can see that efficiency is just not my strong suit. And then that means that this goes away. And now the only challenge is bringing this here. So we could pull that all the way up. Well, all right, I'm going to stop worrying about efficiency. We'll just do that. Actually, what I know is they're drawing a square, right? So therefore, it would actually be more efficient. I know I said I will not worry about it. Obviously, I lied. It would actually be a little more efficient to do this. Because then the square will be smaller, I think. That looks right to me. Let's try it out. So far, so good. Yeah, that's our solution. There's our electronic lock. Motor controller. When on is activated, motor should be turned on until off is activated in a later cycle. Hint, you'll need to create a circuit that can keep itself on to remember between cycles. I vaguely remember these circuits from Constructor, Engineer of the People, and I hate them. They're painful, right? So we know, my recollection is that it's something vaguely akin to this, but not exactly. So off is going to be controlling our gate, right? Like we know that. That has to be. And then that's the output that controls the AND. On controls the AND, right? So we're going to turn on, the time 0 begins. This is already on. No, because it's got to be activated by on. So therefore, this doesn't have power yet. Right. Okay. Yeah, I remember this. I hate this so much. That goes away. This is so crazy. I hate this. Did I mention I hate this? I hate this. Right. Looks great, don't it? All right. Now, right, it's flowing basically the other way here. So we have power here always. Okay. That means that this power is flowing, right? And then this goes to the motor. Let's step through. Okay. So cycle 0, we have power coming in here. Our NOT gate is not activated, right? So power is going to go into here, I believe. Right? Power goes into here, comes through here. At that point, our on button is pressed. And now this side of, which is this side of this transistor here, it's actually the right side of both of these transistors. It's the right side of the and the NOT. That finally powers the motor until and unless it's oscillating. We don't want to be oscillating, do we? No, I've done something wrong. Oh God. I don't want to do this. No, this is unholy. No, no, that's not right. Mankind was not meant to do these sorts of things. Ooh. So what we're doing here is we're bridging. If we leave that as an isolated bridge, then it is in fact just an oscillator. But by bridging it also with the right side of this, what we're doing is basically forcing it up until and unless this NOT gate goes. It's I hate this. This circuit, this is the one that broke me. I don't know, maybe I won't do part 3 after this one. This hurts. Anyway, if you would like to give a better explanation than I did, please leave a comment down below. Please feel free to like and subscribe to this channel. It really does make a difference in getting the word out. If you want me to make more of these extremely nerdy videos, that's what keeps me going. So thank you very much. This has been Gaming Like It's 1979. Thanks for watching.